Hi everyone, I'm Shouqian from SIGMETRICS'2020. I will talk about Ludo hashing, a compact and dynamic key-value lookup for practical network systems. It's a joint work with Professor Chen at SIGMETRICS'2020. Let's start with an example. Network forwarders, switches or routers, are connected with each other to form a network, and hosts are connected to the forwarders. When a network packet or a message is being forwarded between two hosts, each forwarder decides independently which port to send out the packet. And for the same packet, if a link encounters a physical failure, a detour should be taken. This forwarding works because each forwarder stores an ID to port mapping, and each packet is looked up in the mapping to get the outbound direction identified by the port number. A control machine maintains the full states of the network and the full mapping for the forwarders. It monitors the topology changes and computes proper updates for the mapping. The delta update messages are sent to the forwarders to reflect the essential updates. Thus, the route is changed accordingly. The requirements of the mapping are threefold: compact, dynamic, and fast, which mean low memory cost on the lookup program, fast to update, and high lookup throughput. As another example, suppose we have a set of storage machines storing data objects. To fetch the data object for a given key, the indexing programs are required to receive the data fetch request and forward the request to a proper storage machine. We also require the indexing algorithm here to be compact, dynamic, and fast. Key-value lookup engines also find their way in many other networked or distributed systems, including but not limited to the resource locator in the content distribution network, the connection to server mapping in the cloud load balancers, the translation table in the network address translation. And IoT devices may also require key-value lookup in data sharing, certification, verification, etc. Compact, dynamic, and fast are common requirements for the key-value lookup programs in the above systems and even more. Hash tables are traditional solutions to the key-value lookup problem for its constant lookup time. Traditional hash tables mainly fall into two categories: the chaining style and the proving style. The lookup for both algorithms are similar. First, index this key via a naive hash function and resolve collisions via chaining or rehashing. Key collision is really bad for hash tables. On one hand, it introduces a trade-off between lookup complexity and memory utilization. And on the other hand, distinguishing one colliding key from the other requires storage on the keys. Cuckoo hashing partially solves the collision problem by limiting the number of colliding keys. A popular version of cuckoo hashing is 2-for cuckoo, which is associated with the two hash functions h0 and h1. The table space is organized as buckets and slots, where there are 4 slots per bucket, and the proper number of buckets to hold the key-value pairs. As an example here, 18 key-value pairs are placed into 5 buckets and 20 slots in total, with 2 empty slots. We skip the construction of the 2-for cuckoo and show how it works via the lookup process for a key k. First, the hash values h0k and h1k are calculated, and then the bucket number h0k is visited. K is compared with each key in the 3 non-empty slots in that bucket. The associated value is returned if there is a match. If no luck, the bucket indexes h1k is visited to perform the second try. If none of the 8 slots matches k, k is invalid. The 2-for cuckoo works out great in many practical systems because it bounds the number of collisions to no more than 8, which indicates a guaranteed constant lookup time. However, it still needs to store the keys to resolve the collisions, which takes a lot of memory space. The question is how to resolve the collisions while maintaining minimized key information. Minimal perfect hashing works in another way and addresses both the unbounded lookup time and the full key storage problems. Imagine we have a collision-free hash function f which maps a set of keys into different locations, again, guaranteed without any clearing. If we use this special function as the index into the value array, then we successfully avoid storing keys. Of course, this hash function should be smart enough and very specific to the key set. The ideal minimal perfect hash function has constant lookup time and very low memory cost to represent the function itself. However, if the key set updates, the function should be recalculated, which means minimal perfect hashing is rather static and it suffers from key set dynamics. So we further ask how to store or minimize the key information while allowing dynamics. We propose Ludo hashing, which resolves the key clearance perfectly and supports changes of the key set. Ludo costs less space for the key value lookup by storing the minimizer info to resolve the key clearance, instead of storing the full keys as done in hash tables. Besides, Ludo allows fast insertions after construction, as opposed to the static minimal perfect hashing. The core idea of Ludo is two-step clearing resolution, with each step minimizing space while allowing key set updates. In the first step, the keys are given at the input, and the proper number of buckets are allocated, such that if each bucket contains at most 4 keys, then 95% of space will be occupied. A mapping is found to realize the bounded clearing. We call the mapping as a bucket locator. In the second step, another mapping is found to perfectly resolve the up to 4 clearance in a bucket. We call this mapping as a slot locator. The slot locator is calculated via brute force. We enumerate on the hash seeds and see the derived hash function can map the 4 keys into the 4 slots without clearing or not. Ludo is designed based on the simple idea, and it minimizes space cost to less than half a byte per key. We compare Ludo with existing dynamic key value lookup algorithms and get this figure. The PK cuckoo here is short for partial key cuckoo hashing. It saves a great amount of memory than 2-for cuckoo hashing by storing the digest of the keys instead of the full keys. However, the partial key cuckoo does not save space for free. It loses some information, and thus key clearance exists. The Ludo hashing, however, achieves the most compact memory cost by replacing the full keys with the direct encoding of how the key clearance are resolved. Ludo leverages a 2-level architecture to support runtime updates. The lower level consists of several identical copies of the Ludo lookup structures, which do not store the full keys and are compact in memory. They serve the lookup requests in parallel. Some external application systems will make queries to the lookup structures and get replies from the lookup structures. The Ludo maintenance structure maintains the full state for the lookup structures, receives the key value update requests from the application system, and construct update messages for the lookup structures. I will show how Ludo encodes the clearing resolution by the following example. A typical Ludo hashing consists of 3 parts: a table body, 2 hash functions, and a bucket locator. The table body is composed of a number of buckets, and each bucket contains 1 seed and 4 values. Keys are not stored in Ludo. Each hash seed is 5 bits in length and generates the mapping in the slot locator. In another word, the slot locators cost 1.25 bits per key value pair. The bucket locator stores a 1-bit mapping for each key and is implemented as an Othello hashing, which costs 2.33 bits per key. Othello hashing is a fast and dynamic lookup data structure published in ICMP 17. Ludo leverages a 2-step clearing resolution by a global bucket locator and the slot locators each for a bucket, and the total overhead is less than half a byte per key value pair. To look up a key, the bucket locator is visited to get the associated bit B. Then B, the value being 0 or 1, is used to select from the hash functions h0 and h1, and bucket number hbk is visited. In the visited bucket, the slot locator is constructed from the seed s, and the value for k is got by reading the slot number hsk without any clearing. Ludo is constructed based on the plain 2-4 cuckoo hash table. Suppose a list of key value pairs, and let's see how a Ludo is constructed from the list. First, the key value pairs are inserted into the cuckoo hash table sequentially, K1, K2, K3, K4, and so on. The placement is subject to the cuckoo insertion process. And you may notice that the final locations of the key value pairs may not be the initial ones, and the cuckoo hashing automatically bounds the clearance for any inserted key within the bucket holding the key. Then, for each bucket, a hash seed is found to resolve the clearance within the bucket. It is achieved via brute force. The non-negative integers are tried sequentially as a hash seed and see if the generated hash function can map the 4 keys to 4 different slots without any clearing or not. Each try succeeds in a possibility around 10%, and different tries are independent from each other. Like in this example, the first bucket succeeds at 16 tries from 0 to 15, and the second bucket, it is lucky and succeeds at the third try. In our experiments, only 2% of the seeds are more than 5 bits, so we set the overflow threshold to 31. The third bucket takes a little bit longer and succeeds at 174 tries, and thus an overflow. We mark it as overflow, and we will resolve this issue later. Buckets having empty slots are easier to build because less clearance are possible. Like the fourth bucket, it succeeds at just 1 try. The brute force search continues until each bucket holds a valid seed. The third step is to build a bucket locator to indicate the bucket choice for each key. An Othello hashing is constructed to maintain that information. So far, we have the complete Ludo maintenance structure, a hash seed for slot locators, a cuckoo hash table, and an Othello. Next, I will show how the Ludo lookup structure is built. First, the hash seeds and the cuckoo hash table are combined to produce the table body in the lookup structure. During this process, values and seeds are kept while the keys are dropped. Besides, values in each bucket are reordered according to the generated slot locator from the hash seed. To achieve maximum compactness, we use bit-level compression for the table body, which means not a single bit is wasted for memory alignment. The overflow seeds, which are no less than 31, are put into an overflow table. This table is small and holds 2% of the buckets in our experiments. Finally, the bucket locator, or the Othello lookup structure, is constructed from the Othello maintenance structure. We skip this here, and please refer to our paper for details. So far, we have covered the following topics for Ludo hashing: the basic idea of two-step clearing resolution, and to encode the 2 clearing resolution steps with minimized information to avoid storing full keys. The lookup and construction are based on the existing 2-4 cuckoo and Othello. Due to time limit, we skip the following topics, which are also significant and interesting: the optimizations towards both time and space for the bucket locator and slot locator, how Ludo supports constant time insertion and deletion, a theory rediscovery on why 2-4 cuckoo always succeeds for insertion under a certain load threshold, how Ludo supports multiple reader and single writer concurrency, optimizations on the parameters, 2 global hash functions, 4 slots for cuckoo, and 5 bits for the slot locator seeds. If you are interested in any of the above, please refer to our paper. We evaluate the memory cost, update speed, and lookup throughput in a single-thread simulation. The experiments are done on the commodity server with 2 Xeon E5 CPUs, 160 GB RAM. This figure shows the memory cost breakdown of Ludo lookup structure, SASAP, Othello lookup structure, partial key cuckoo, and cuckoo hashing, where the number of keys is 1 billion, the length of the keys is 100 bits, and length of the key digest is 30 bits. We set the length of the values as 10 and 20 bits. Clearly, Ludo hashing needs the least memory cost among all the designs for both value lengths. By comparing the breakdown parts of each design, we find that Ludo uses similar space to store the values, which seems unavoidable for each key-value lookup table. Note that Othello embeds the values in the two arrays A and B. Again, the partial key cuckoo gains space saving by replacing the full keys into key digests, while the Ludo further reduces the space cost by using the bucket locator and slot locator to replace the key digests, while SASAP shows comparable memory cost when the value is 10 bits. It is hard to update to our knowledge. We evaluate the update throughput of Ludo hashing, Othello hashing, and SASAP, which characterizes the maximum number of updates a table can support in the unit of millions of operations per second. All experiments are performed in a single thread with equal number of insertions, deletions, and value changes. We set the length of the keys to 32 bits and length of the values to 20 bits, change the table size, and show the results. The results show that Ludo and Othello allows more than 5 million operations updates per second, while the SASAP performs more than 1,000 times worse than the other two, even if we only consider the updates that do not cause the reconstruction for the SASAP. This figure showed the lookup throughput of Ludo under concurrent updates by varying the update frequency and the number of lookup threads, where the length of the keys is 64 bits, and the length of the values is 20 bits, and the number of keys is 16 million. Our observation on this figure are twofold. On one hand, the parallel throughput for Ludo scales linearly with the number of threads. The second, that there's no noticeable throughput degradation when the update frequency grows up to 1.6 thousand updates per second. We also evaluate the lookup throughput of Ludo in a case study for indexing distributed contents. Experiments are carried out in the real network on Cloud Lab with Intel DBTK enabled. The experiments use two machines, both with two Xeon E5 CPUs, 160 GB RAM, and a dual-port 10 gigabit per second NIC, which supports up to 20 gigabit per second bandwidth. The two machines are connected back-to-back via a 20 gigabit OpenFlow switch in layer 2. We run a real network indexing server based on DBTK. The throughput is evaluated in terms of million packets per second, and the packet size is 45 bytes. The maximum throughput is bounded by the bandwidth of the NICs, 20 gigabits per second in total. The single-thread Ludo outperformed other three and reaches the maximum bandwidth. The reason Ludo outperforms others is that the bucket locator of Ludo hashing is compact enough to fit into the last level cache, so that for a single lookup, it is likely to have only one load from the main memory for the table bucket access. Other solutions, however, have two or more memory loads. This figure shows the throughput for two threads in the DBTK. Ludo reaches the bottleneck of the NIC, and other three algorithms show improvements near 2 times. As a conclusion, we propose Ludo for compact, dynamic, and fast key-value lookup for practical network systems. Instead of storing full keys to resolve the hash clearance, Ludo encodes the two-step clearing resolution for minimized space cost while still supporting post-construction updates. Ludo is the most compact key-value lookup algorithm to our knowledge, with negligible cost on runtime insertions, deletions, and value changes, and is able to scale linearly for the lookup throughput. Besides, the runtime updates can be done concurrently with the lookup queries. We believe Ludo has its advantages in many application systems. If you are interested in more details, please feel free to refer to our full paper and contact us via email. Please feel free to try our implementation of Ludo on this link. Thank you for listening.